In this lesson, we are going to learn how virtual threads actually work. First, I'll explain the basic concepts, then gradually I'll demonstrate them with sample programs. In a system with multi-core CPUs, the operating system can schedule different OS threads or OT to run concurrently on different CPU cores, which actually enables true parallelism. So here in the diagram, I'm just showing there could be multiple OS threads which can be run on multiple CPU cores in case those are available. And this scheduling is performed by the OS scheduler. Now it varies based on the operating system we are working. The classic Java thread or the platform thread, which I'm depicting here using this arrow called PT, is a thin Java wrapper around the OS thread. Basically, we have 1:1 mapping between every platform thread and operating system thread. This platform thread scheduling is also performed by the OS scheduler. These platform threads are heavy because they have fixed size stack, which is generally 1 to 2 MB depending on the OS. They're very less in numbers, few thousands. As we know, platform threads have one-to-one mapping with the OS threads, so creating them in very high number would be problematic. It is scheduled by the OS scheduler, which is preemptive in nature, which follows the time sharing principle. In a specific case, if a platform thread is running for a long time, the OS scheduler can detach that platform thread and bring in other platform threads so that that could be run on top of the CPU core. Now, from Java 21 onwards, we have virtual threads. Virtual threads are light, they have resizable stack, and the size is very less, around 1 to 2 KB. We can create large number of virtual threads. It could be 100K to few millions even. They run on CPU via the platform thread, which we call carrier thread. Suppose a virtual thread is running on top of a platform thread, then that particular platform thread is called the carrier thread of that specific virtual thread. Virtual threads are scheduled by JVM scheduler, or we call it virtual thread scheduler, which is non-preemptive nature, which works on collaborative model. Now, this is a very important difference between the platform thread scheduler and the virtual thread scheduler. Platform thread scheduler, as we discussed, is preemptive nature. Based on scenario, it can detach the platform thread and bring in other platform threads to the CPU core. But in case of virtual thread, the scheduler itself cannot detach the virtual thread from the platform thread. That is a very important difference, and we will explore that further later in this lesson. Now, if we discuss further regarding the virtual thread scheduler, as soon as we create one or more virtual thread under the hood, the JVM creates a small internal pool of platform threads, which is basically a ForkJoin pool. This dedicated work stealing ForkJoin pool is managed by JVM and serves as a virtual thread scheduler with a FIFO, first in first out queue. Its initial capacity, that is the number of threads, is set to match the number of available cores, and max it can be increased to 256. Here in the diagram, hypothetically, we have kept 4 CPU cores. That is why we are displaying the ForkJoinPool default size is equal to the number 4. Now, do not confuse this ForkJoinPool with the one we generally use for parallel streams, the common ForkJoinPool, which is ForkJoinPool.commonPool. This ForkJoin pools could be configured via different configuration parameters or programmatically as well. It can be configured with the following system properties, and these properties are like jdk.virtualThreadScheduler.parallelism. The pool size, how many carrier threads, defaults to the number of CPU cores. So by default, its value is equal to the core we have in the system. We can change it based on our requirement. jdk.virtualThreadScheduler max pool size. This is the maximum size of the pool by default, which is 256. The number of carrier threads can exceed temporarily the number set by parallelism value when the carrier threads are blocked. jdk.virtualThreadScheduler min runnable. This is the minimum number of threads that are kept runnable in the pool. Now we are back to the original slide where we had virtual threads platform threads, OS threads, and the cores displayed. I'm going to change this visual a little bit. This JVM, I'm going to logically segregate into two parts. One is the JVM and the application. The application itself would be running on top of the JVM, but for the sake of simplicity, let me divide it. Now, if I think of a sample application which is running on top of the JVM, and if we create a virtual thread and try to run it, what will happen? The process that will take place now is called mounting. When the Java runtime, basically the virtual thread scheduler in this case, schedules a virtual thread, it assigns or mounts that particular virtual thread on a platform thread from the ForkJoinPool. Now the virtual thread is mounted on top of the platform thread, but the platform thread also needs to be scheduled. That scheduling is done by the OS scheduler. Now, when this virtual thread is mounted on top of this particular platform thread, this platform thread is called the carrier thread of the specific virtual thread. Now, if the virtual thread gets blocked on a blocking operation, maybe it's an IO operation in the Java code, then the carrier thread or the platform thread is released. This process is called unmounting. This way, the carrier thread can execute any other eligible virtual threads which are in runnable state. Now, once the blocked virtual thread finishes the blocking operation, the scheduler schedules it again for the execution. The execution can continue on the same carrier thread or a different one based on the availability of the carrier thread. There is no affinity basically. So now, if this virtual thread is again ready, it can schedule on top of any available carrier thread. So here I'm just showing another virtual thread got mounted on the previous platform thread and the old one is getting mounted on top of another carrier thread. Once the execution for these virtual threads are done, again they would be unmounted. Now, what are the basic scenarios when the virtual threads are actually blocked? From an application, if there is any API call, this API call could be some external API call or some external microservice call. This could be blocking like API call. Any database query also could be a blocking call. Both of them are actually network calls. Apart from this two, file read and write, they can be also blocking, and based on different scenarios, based on the implementation usage of reentrant lock or semaphore or barrier, this different concurrency control related stuff, they can also block the virtual thread. So using different virtual threads, when we perform such operations, they could be blocking in nature and they can result in the unmounting of the virtual thread from the carrier thread. Now the concepts that we have discussed so far, let us understand them with practical examples. To get started, I have a sample program over here, virtual thread mount unmount. Let me maximize this. Here, initially, I'm defining the number of threads that I'm going to create. I have a sample runnable task with log and sleep. Inside that, I have two custom methods. One is log, another is sleep form. Let me go inside this method. Inside log, we are passing a message. It is taking the current thread object and then it is printing the message, the thread name, whether the thread is virtual or not, and then the thread object. Similarly, if I just check this sleep form method, which I am calling inside the runnable task, I have a thread.sleep invocation where based on the amount and the unit passed, the thread is sleeping over here. So let's go back to the beginning. After this task creation, I have a list of threads. Then there is a simple for loop starting from 0 to number of threads, that is 10 times. We are creating virtual thread using thread.offVirtual.unstarted and then passing this runnable task. We are adding this thread to the list. Let me scroll down. And here we are starting all the virtual threads by iterating on top of the list and then joining them to the main. So here we are creating 10 virtual threads. For those 10 virtual threads, we are just going to check what are their names and what are the associated carrier thread names. Let's find out. Let's run this. Maximizing this one. So here, if we notice, as we have not passed any thread name over here, the thread name is blank. But when we are printing the object using its toString, we can see it is showing virtual thread, then the ID assigned to the virtual thread by the JVM, their state, then the ForkJoinPool name, and then the carrier thread. So here I can see to different virtual threads, 4 carrier threads are assigned. If you recall, by default, the number of carrier threads that should be present in the ForkJoin pool should be equal to the available processes within the system. So let me print out the number of available processes over here. Just added this line, runtime.getRuntime.available processes. Scrolling up here, we can see in my system, number of available processes is 4. That is why it is assigning 4 carrier threads to the ForkJoin pool. Now, if we go through this logs over here, we have this 10 threads. And if I have a look at the logic over here, we have this sleep for invoked. Now, as inside sleep for, we have this call for thread.sleep. All of them would be unmounted. After the sleep for, if we add another log, then we can see what carrier threads are attached to that particular virtual thread. Let me add another log over here. If we think about the execution logic for a particular virtual thread over here, when it starts, this log function does not have any IO call. Sleep, yes, we have thread.sleep over here. So it would get unmounted. Now later on, when it is remounted, then only again it would execute line number 21. That is why I have written after remount. Let me run this again. So here for virtual thread number 21, initially it was using this carrier thread worker 1, but after remount it is using worker 2. After remount, it could be assigned to the same carrier thread or a different carrier thread based on the availability. One important thing I want to show you over here, in case of virtual thread, this unmount would happen in case of IO based tasks, not CPU intensive tasks. If I go to this sleep for method and click on this thread.sleep, let me maximize this. You can see there is a simple if-else logic inside thread.java where it is clearly checking whether it is an instance of virtual thread or not. If it is virtual thread, then it is invoking virtual thread.sleep nanos method. If it is not, then there is a separate logic. Let me go inside this sleep nanos. Inside sleep nanos, if I do a control click on this park nanos and scroll down a little bit, we have a try block over here which invokes yield continuation. Let me click on this. This is the part where the logic is written for unmounting. You don't need to go through all the details, but this is the core area where unmounting logic is present. And this specific part, continuation, it is a separate topic for discussion, which I would cover in the later lessons. But for mounting and unmounting, this continuation is heavily used by JDK for virtual threads. Now, going back to our original program, I want to show you few separate things as well. Here, we are starting the different threads. Let me put a breakpoint over here and run this in debug mode. Now here, if I resize this, this is the list of thread objects. If I expand, all of them are in new state because none of them are started. Let me click on this resume button for a few times. I can see the first one is in runnable state. Let me drag this a little bit, expand this. We have the scheduler associated with this. Now for all of these virtual threads, we are using the same scheduler, right? The same ForkJoinPool. It has parallelism 4. And here we can notice the carrier thread that is associated. Let me expand this. Here we can see the pool that is mentioned, the name prefix basically, and many other details. By default, the parallelism is 4. We can customize that as well. If I go inside virtual thread class, let me maximize this. Let me search with JDK. You can see over here, it has a method called create default scheduler. And inside that, it is checking all 3 parameters which we discussed earlier. This jdk.virtualThreadScheduler, parallelism, max pool size, min runnable, everything. Now, if I set this to a different value, accordingly, the value of parallelism would change. Let us do that. Going back to our old code, setting this to 8. Let me print this as well. Again, running this in debug mode. Running this loop for a few times, clicking on resume, expanding this. Now you can clearly see, the value of parallelism is 8. So by going through this sample program and going through this internal structure a little bit, we have now a basic understanding like how this mounting and unmounting works, how this fork join pull works. Let me stop this program Now, if we just recall what we discussed regarding this ForkJoinPool, what is its parallelism, we have seen them hands-on. We have also seen mounting, unmounting, and remounting. Now, I have another sample program where I will demonstrate how this mounting and unmounting works differently for IO intensive operations and CPU intensive operations. As we discussed earlier, in case of IO based operations, whenever there is a blocking call, unmounting would happen in case of virtual thread. But in case of CPU based operations, that won't be the case. As the virtual thread scheduler works in a collaborative manner, it won't unmount itself like it did for blocking calls. Let's check that out with a sample program over here. Closing all this. Here I have written two custom classes. Let me open this virtual thread profiler. So in this class, what I'm trying to do, I'm trying to monitor the unmounting of the virtual threads. I'm not going through line by line for this code, but I'm showing you the main area. So if you have a look over here, this is the method profile. Here I'm taking one task ID and a task. So before the task runs, I'm registering the start time and the thread name. And then I'm invoking task.run. Similarly, after that, I'm capturing the end time and the thread name. Now, if this call is from a virtual thread, we know when it started, what was the carrier thread. We can extract the carrier thread name from here. And after the run as well, we can do the same thing. Now, if it is a blocking call, definitely it would unmount, and the carrier thread name that we extract from here, high probability it would be differ. It is possible that the same virtual thread, even after unmount or remount, get the same carrier thread, but in many cases the carrier thread names would be different. After that, I have the logic to extract the virtual thread name and the carrier thread name. So here I'm preparing a string where I'm just printing the virtual threads where the remount happened on the same carrier thread and where the carrier thread got changed. That is the main logic over here. And also, to show the task progress, I have a sample method where I'm printing asterisks based on the time it is pending. So this virtual thread is kind of a wrapper on top of a runnable. If I show you the example over here, this is the demo class virtual thread mount unmount with custom profiler. So here I'm creating this custom virtual thread profiler object over here. Inside main, inside try block, we are creating one executor service using executors dot new virtual thread per task executor. Based on the number of tasks, what we are doing, we have a runnable object and then we are submitting this runnable. Here if you see, we are passing a task ID and this runnable object to my profiler. So inside profiler, what we are doing, we are just capturing the information before the task run and after the task run, how much the time was taken and what was the carrier thread name. That's the thing. And also we have the logic to print the progress bars when the virtual thread is getting executed. Here I have two methods. One is for simulating blocking IO logic, another is for CPU load. Let me go into this method. It basically has only thread.sleep for 500 milliseconds and the CPU load. Here I'm just doing simple computation using big integer so that when this method is called, our program performs some CPU intensive operation. Let me go back to the original logic. So here at a high level, what would happen? 50 virtual threads would be created. All of them would be executing one particular task and that task would be IO intensive. Let me run this. So it has finished execution. Now here, what we can see, these are the different tasks. This is the progress that I have printed. And for all these threads where I have this check, before remount and after remount, the carrier thread names are different. For this virtual thread 21, it was worker 1. It went to worker 3. Same for all these three. For some of them, say for this one, even after remount, it got assigned to the same carrier thread. Now this is purely based on availability because there is no affinity between the virtual thread and the carrier thread over here. So we can see all this task got executed and we can understand for which it changed the carrier thread and for which it did not. Now what would happen if the task is CPU intensive? We discussed, right? For CPU intensive tasks, there won't be any unmount unless the task itself gets completed. Let's check that out. I'm commenting this out, enabling this simulate CPU load, running it. It's waiting for the virtual thread tasks to complete. Now the program has ended. If I scroll up, the entire thing is different over here. We can see there is no unmount as we discussed. And also, as we have 4 cores available, all the 4 virtual threads are getting executed and completed, and only then another 4 are taken. As expected, there is no unmounting. All of them are finishing on the same carrier thread. And another thing to notice over here, if we look at the progress, first all 4s are getting executed, only then another 4. After that, remaining 4. As the carrier threads are blocked, unless the execution of the virtual threads CPU intensive task is complete, unmounting is not there. Hence, we are not getting the parallelism to the level we are getting for IO intensive operations. So, this is the basic difference for IO intensive and CPU intensive tasks in virtual thread. So, it is demonstrating the very basic difference in terms of execution of CPU intensive tasks and IO intensive tasks in case of virtual threads. When we were using the IO intensive one, as all of them were getting unmounted, all of them were running parallelly. Let me just quickly show you again over here. Here you can see for all 50 of them, they could run parallelly, but it was definitely not the case for CPU intensive ones. First 4 got finished, then another 4, then another 4. That way it progressed. If you found this lesson useful and want to go deeper with virtual threads, structured concurrency, scope values, and their real-world usage with Spring Boot, I have created a complete course on Udemy, Java virtual threads, and structured concurrency with Spring Boot. In this course, I have covered all the advanced topics like virtual thread mounting, unmounting, virtual thread pinning, monitoring this with JFR, Micrometer, Prometheus, Grafana, and performance testing with JMeter. In case you are interested, you can check out the link in the description. In case you need discount coupons, I have provided all the contact information in the description as well. I would request you to hit the like button if this video has helped you and subscribe for more content like this one.